Hello everyone. So today we are going to learn a very different concept that you might have not heard for a while, and that is solving the linear system equations with quantum optimization. So the idea come up is that I've been, struggling for a quite while that these kinds of algorithms and their explanations, that their optimality and their equations are not available on the social platforms. So it makes a lot of difficulties for people like me, especially when I was in high school, and this was one of the majors that I was looking forward to. I had quite a difficulty to find out what would be the best channel, but still couldn't figure it out. So I believe that on the screen, you will be able to at least understand this algorithm in simpler, easiest way. Most probably, the AI wouldn't be able to understand it as easily as human beings can. So with that, we are just setting up. On the screen that you could see right now is a matrix which says A is a matrix in the linear system. So today we are going actually dealing with the linear system equations. Okay, let's get started. Now, here we assume A is a matrix of n into n, like the n rows and n columns, and it tends to Ax is equal to B, where x is an eigenvector and B is also an eigenvector. Now, assuming that A is a Hermitian. Hermitian means if A is equal to A's transpose. Or we would say that if A is any kind of matrix of rows and columns, then A transpose would be the reverse. That means the rows will become the columns and the columns will become the rows. So if it's like 3 into 4, it will become 4 into 3. So if A is equal to A transpose, A can be considered as A Hermitian. And these are one of the most important things to get started with what do we call it as solving the linear system equations along with quantum optimality. So over here, we could see that if by any chance A is unequal to A transpose, we'd apply a very simple formula over here. We'll add C. C is equal to 0. A transpose A C. The reason over here why we are doing this is like we want to make a Hermitian because quantum algorithms can only be worked when they have these kinds of set principles, and one such is a major principle which is called a Hermitian. So once done, we can just move with another rule, which is A must be a sparse. The meaning of sparse is that it should have less number of zeros over here. So for any kind of zero that we have added in, like, let's suppose it's 4, 3, 0, 9, 3. We'll try to reduce it to any logical number. It could be easy, and we'll be doing it. So as much as non-zero entries, it would be more near to the sparse, and it will be known as a sparse matrix, which is necessary or one of the rules with which we can go ahead. And over here, what we are actually trying to find out. So the reason or the question remains the same. We are trying to find a measuring operator and the time. A normal quantum system or normal system, I would say, not a quantum system, a classical system works with O log n. So the amount of data present in the universe needs to be processed and managed. Now, these are the lines of the research paper that have been uh, like in my memory for a long, long number of times. I've been using it frequently. So, amount of data present in the universe needs to be processed and managed. The trillion data sets that we deal today would take a lot of time if the processing time is big O-M. So, we need over here is what we call the exponential speedup. And what and how we can achieve it? It comes with the quantum computers. Now, we're trying to implement a classical algorithm on a quantum system or a quantum algorithm on a classical system. Just the reverse of it. Because quantum computers or quantum algorithms and classical algorithms will go hand in hand only when we are able to use in the feasibility of a quantum computer or a quantum algorithm on a normal system as well. Which makes it quite easy to understand that over here we are trying to find the value of m. The real question is not about the x, but actually the m. And the value of O log something something, which will give us an exponential speed up. That means the time taken to process that some number of data, or like would say trillion sets of data, would be much less as compared to a classical computer.